And this relates, of course, to the problem of ion rotations in quantum theory as well, and this notion that we may well not need rotations in quantum theory. I'm desperately trying to figure out this quantity omega g because this pertains to dark matter and the resistance between gravitational fields. So we can consider, of course, a given gravitational field to be this quantity ρ2, this secondary electron density, whereby I was providing definitions or parameterizations of ρ1 versus ρ2 in terms of van der Waals radiuses. So every electron that appears prior to the van der Waals radius of an atom, that would be in the primary electron density of the atom. However, ρ2 is this invisible part beyond the van der Waals radius that we can't really see, or that we may tentatively observe with electron microscopes, or we can infer the presence of ρ2, but we can't. We can, obviously sort of detect it, you know, well, indirectly, if you see what I mean, with our experiments and observations of gravity and gravitational forces. Well, I mean, the thing about ρ2 is it shows up even in electrostatic interaction. So when you have those sorts of experiments where you get a balloon and rub it and it bends water. And the electrostatic forces from the balloon cause the water's trajectory to change. That's also an effect of the secondary electron density, or the secondary, the gravitational field, really, or the gravito-electrical field, or the gravito-electroweak field, if you like. But I'm very much still. This is like the equation to figure out ρ2, if you know what I mean. I'm just using this symbol alpha not to denote the fine structure constant, but to denote this ratio 4.17 times 10 to the minus 42, because it's just easier than writing that out all the time. And I thought that's a nice, neat little equation, and that's the time-independent value for ρ2. However, when it comes to ρ2 in a time-dependent reference frame, you do need that, I think, to incorporate these L and P quantities, these quantities of linear and angular momentum. And I've come up with some very fruity equations for these before, but nothing ever has really struck me as satisfactory so much. And I've certainly been unable to do what Feynman, of course, tells us is crucial with crafting any kind of mathematical equation. We must be able to get a quantity out of it at the end that reflects, for instance, resistance in ohms or something like that. And we must be able to get a quantity that's measurable with a unit of measurement at it at the end of it, at the end. Otherwise we haven't done anything, right? We haven't, we're just jumbling symbols together then, or showing relations between things. And those might have mathematical significance, perhaps, if we're not, just doing like pictures with maths or something. But then again, maths should be able to show pictures, or if it's not like a sort of poem with mathematical symbols or something like that. But I've also come up with this neat little equation for the force of gravity. Force of gravity being the force of electromagnetism or electrostatic forces plus radiation pressure. So I thought this was a really neat, really nice little equation. I like it so much, actually. I'm going to put a whole little box around it, just to remind me of the significance of this, and the significance perhaps of this discovery. And this comes out of my considerations given to, in all these sorts of calculations with Coulomb's law and so on, trying to, calculate the force of gravity between two hydrogen atoms in a box in terms of Coulomb's law and in terms of Newton's law of universal gravitation, taking the first the force of gravity between between two hydrogen atoms, and then taking the number of electrons, right, entering them into that equation, multiplying the result of that equation by the charge of the electron, then imputing that into Coulomb's law with the charge of the proton, or the protons, in the box. So it's 2 protons, of course, in the box and 2 electrons in total. But what you get out of this, you don't get the charge of the electron out of it. You get a much smaller number. So then if you multiply that by the charge of the electron, you get the value of all the secondary density electrons, which is the electrons we're really interested in when we're studying gravity. And then, lo and behold, we get, where's it gone? Stupid papers everywhere. Here we go. Yes, here we go. We get these 2 quantities, right? So we get this quantity, which is less than this one, of course. This is the one from Newton's law. This is just the bare force of gravity apparent between 2 hydrogen atoms in terms of their mass. However, this is the force of these assumed charges of secondary density electrons, right, between the secondary density electrons and the protons in the nucleus, the nuclei of those 2 hydrogen atoms, and it almost measures up. So we don't quite have this huge rift anymore between the electrical forces and the force of gravitation. What we have is something that is getting closer to it, but it's not quite there. It never would be. There's this gap between it. There's this very interesting little gap which is filled with radiation pressure, and that's what the term P gamma in my last dinky little formula, if you know what I mean, F grav equals F elec plus radiation pressure. That's what that signifies. So what the F elec stands for electrical force or electrostatic force. So force of gravity equals F elec plus P gamma. It is, of course, not that simple. That's a good approximation of it. That's like sort of saying like E equals mc squared, whereas it isn't really E equals mc squared. It's E squared equals P squared something C to the 4th and so on. And P squared T squared plus T squared minus, no, never mind, I can't remember what it is, the full equation for Einstein's, well, equivalence relation, is it not? Yeah, the strong equivalence principle, I believe. Yeah, but I thought that was a nice little equation. It tells a lot, I think. It tells a very good story. These are just gumph, I think. This is very nice. This is very nice and neat. I'm sticking with this one. I'm happy with this. I like a good equation. Nice and chemically with your average atomic number. Nice and quantum-y with your fine structure thing. Thank you for watching, everyone. Bye, love you lots.